Okay, that question came up again about conservative versus non-conservative forces. We've talked about it, we'll talk about it again. Got this little disc here, and I'm going to push it from here to here. Now, what's the direction of my displacement? Obviously that way. What's the direction of the frictional force? This way. So friction did positive or negative work on this?
Negative.
Negative, because the force and the the force and the displacement were in opposite directions, right? Okay. Okay, now I push it back. What's the direction of my force? This way. What's the direction of my displacement? This way. Again, that force does negative work on the thing, right? Okay, so the frictional force from here to here and back to the same point did negative work. Both directions, right? Okay? So that there was a net negative work by the frictional force, even though I came back to the same point. Okay, we're going to see a contrast there with what the gravitational force does. Okay, well, would you say that the frictional force is path independent? As I go from here to here and then from here to here, do I have the same frictional force at every point? No, because when I'm going this way, the frictional force is this way, and when I'm coming back this way, the frictional force is this way. The frictional force is not path independent. Okay? And notice the frictional force over a path that ends up where it started was not zero, was it? Now, if I lift this thing up and then bring it back down, okay, well, as I'm going up, what's the direction of the gravitational force? Downward. Come back down, what's the direction of the gravitational force? Downward. So it has the same direction, and I didn't move significantly further from the center of the Earth, okay? The gravitational force didn't change in magnitude either. So the gravitational force is path independent, at least on this path, and it is on any path, as we'll prove in multivariable calculus in a few weeks when we get to talking about gradients and define conservative forces. And everybody that's not multivariable has to take our word for that, but gravitation is a conservative force. It's a path independent force. That's what a conservative force is. Friction is not conservative. Gravity is conservative. Okay? So it's a force between two magnets or between a magnet and an object that responds to the magnetic force. Okay? Ferromagnetic material, whatever. An electromagnet. Make sense? Those are two examples of conservative forces. Another one is a spring. Okay? Now, we're talking about an ideal spring. If I elongate a spring, what's the direction of the force as I move from here to here? It's back this way, right? Okay, and then as I let the spring come back, what's the direction at this point?
Still the same?
Yeah, as long as I'm below the equilibrium position, it's still upward, right? So if it's downward, if it's upward from here to here, it's upward from here to here. And at the same point, it's the same force. Doesn't care whether I'm going down or up. The only thing that determines that force is the elongation of the spring, right? That's another example of a conservative force. Okay? Now, the implication, if I toss this thing up in the air and catch it at the same point that I tossed it from, its kinetic energy won't have changed. I mean, its kinetic energy at this point was the same when I tossed it as when I caught it. Okay? A mass on a spring that I'm not interfering with, ideal spring, forget all non-conservative forces. Okay? It's going to have the same speed passing this point on the way down as it does on the way back. Okay? To the extent that the force is really conservative. I mean, it never actually is. And all those are implications, so let's talk about that.